Hello, Silicon Architects. Welcome to another electrifying session on your gateway to the cosmos of VLSI. I'm your VLSI buddy, your guide on this intricate journey where we turn silicon into circuits. Today, we're diving into a critical juncture in the VLSI Physical Design. Physical design marks the transition from conceptual design to a concrete, manufacturable blueprint in VLSI development. It involves meticulously arranging, connecting, and verifying the circuit components on silicon to balance performance, power consumption, and area. This process is where theory meets reality, translating a logical design into a precise physical layout, ensuring that the chip operates efficiently and reliably in the real world. Let's dive into the ASIC, application-specific integrated circuit design flow, which is a specialized process within VLSI focused on creating chips tailored for specific applications. The flow begins with defining the specifications, outlining the chip's functionality, performance requirements, and design constraints. Next, we move on to RTL, Register Transfer Level Design, where we describe the chip's behavior using hardware description languages like Verilog or VHDL or UVM. Once the RTL is finalized, we proceed to synthesis, converting the high-level design into a gate-level netlist composed of logic gates and flip-flops. This is followed by the physical design phase, where the logical design is mapped onto the silicon, involving steps like floor planning, placement, and routing. After the layout is complete, we conduct thorough verification through design rule checks, DRC, layout versus schematic, LVS, and timing analysis to ensure the chip meets all design and manufacturing specifications. Finally, the design undergoes sign-off, making it ready for fabrication. Throughout this flow, various tools and techniques are employed to optimize the chip for power, performance, and area. By the end of this video, you'll have a solid understanding of how a custom ASIC is brought from concept to reality. Now let's see what the basic physical design flow stages involve. First is synthesis, followed by floor planning, then placement, after which we go for clock tree synthesis, CTS, that is routing the clock nets with min skew and insertion delay. Next up is routing, which involves routing the signal nets. Once all this is done, we do the design rule check, DRC, and layout versus schematic, LVS, and more importantly, timing closure, aka static, timing analysis, STA, and then we do physical verification, PV, after which the design or the GDS2 file is ready for fabrication. Physical design flow synthesis. Let's synthesize not just circuits, but some real knowledge, shall we? Before we jump into the nuts and bolts, let's get our bearings. Synthesis is that magic wand in the VLSI flow, where high-level design meets reality. Think of it as translating the blueprint of your skyscraper into the actual bricks and mortar. But instead of buildings, we're crafting digital circuits. So, what does synthesis really do? At its core, it takes RTL code, that's register transfer level, the high-level description of your circuit, and converts it into a gate-level netlist. Think of RTL as your circuit's DNA and synthesis as the process of expressing that DNA into actual cells, or in our case, gates. Of course, like any craft, synthesis requires tools. The industry's favorites include heavyweights like Synopsys Design Compiler or Fusion Compiler and Cadence Genus, etc. Synthesis isn't just about translating code, it's about optimizing. Here's where the real challenge lies: balancing timing, area, and power. Imagine you're a juggler, and these are your balls in the air. Push too hard on one, and the others might fall. Timing constraints, area budgets, and power limits are all critical, and synthesis tools offer various levers to tweak these parameters. So, there you have it, folks. Synthesis is where your VLSI design starts to take tangible shape. Next up is floor planning, which is the first step in the actual layout process. In floor planning, we decide the placement of major blocks or macros on the chip. Think of it like laying out the blueprint of a building. You need to ensure that each block is placed optimally to minimize wire length and avoid congestion. This stage also involves planning for power distribution and creating a basic power grid. Once the floor plan is set, we move on to placement. Placement involves positioning the standard cells, which are the basic building blocks of your design, within the floor plan. The goal here is to minimize wire length and ensure that the design meets timing requirements. Placement is critical because it directly impacts the efficiency of routing and the overall performance of the chip. After placement comes clock tree synthesis or CTS. In this stage, we design a clock distribution network that ensures the clock signal reaches all parts of the chip simultaneously. The goal is to minimize clock skew, which is the variation in clock signal arrival times at different components. A well-optimized clock tree is essential for the proper functioning of the chip at the desired clock frequency. Now let's dive into the next category, routing. Routing is the process of connecting all the placed cells with metal wires according to the netlist. There are two main phases in routing: global routing, which determines the general paths for the connections, and detailed routing, which defines the exact paths for each wire. Proper routing is crucial to avoid congestion, meet timing, and adhere to design rules. With routing completed, we move on to verification stages, starting with DRC and LVS. Design rule check. DRC ensures that the layout adheres to the manufacturing rules like minimum spacing between wires. Layout versus schematic. LVS verification checks that the physical layout matches the original schematic, ensuring that after verification, we perform timing analysis and optimization. This step involves checking the design against timing constraints to ensure that all paths meet the required timing. If there are any violations, the design is optimized, possibly by adjusting placement or resizing cells to achieve timing closure. This is crucial for ensuring the chip operates correctly at the target clock frequency. .D sign is correct and will function as intended. Finally, we arrive at the sign-off stage. This is the final set of checks before the design is sent for manufacturing. Sign-off involves running a final DRC, LVS, timing verification, and power analysis to ensure the design is completely error-free and ready for fabrication. Once everything checks out, the design is considered tape-out ready, meaning it's ready to be sent to the foundry for manufacturing. And that's a wrap on the ASIC design flow, focusing on the physical design stages. We've covered everything from synthesis to sign-off, giving you a comprehensive overview of each step. If you found this video helpful, don't forget to smash that like button and let me know in the comments which stage you'd like to dive deeper into in future videos. Also, if you haven't subscribed yet, make sure to do so for more VLSI content. Thanks for watching, and I'll catch you in the next one.